Hey, it's Doc Williams, and in this video, we're going to review how to use ICE tables to solve equilibrium problems. So for this first problem, it states the Kc for the reaction below is 50.5. What are the equilibrium concentrations for all substances if the initial concentrations for H2 and I2 are 1.5 molar? Now, this problem gives us Kc and it gives us the initial concentrations. It's asking us to find the final concentrations, which means we need to set up an ICE table. We already have the equation. If you did not have the equation, you will have to pull the information from the question, write the equation, and balance it because we definitely will need that balance equation in order to solve this problem. Using ICE concentrations, I meaning the initial concentration, C any change in concentration, and E the concentrations at equilibrium. We want to fill out as many values as we can, and then it will help us to calculate anything remaining. So in this problem, we have the initial concentrations for H2 and I2, which we'll write next to initial concentrations, which is 1.50 molar for each. And since it did not give us the initial concentration for HI, we can say this is 0, meaning that this chemical reaction has reactants going into the products, meaning that the change that we will see in the products will be an increase, so we'll write positive, and the changes we see in the concentrations of the reactants will be a decrease, so we'll write negative here. The next step is to determine by how much the change will occur. And we look at our coefficients to determine the degree of change. So since we have a 1 for the coefficient for H2, then this will be 1x. Since we have 1 for the coefficient of iodide, it will be a 1x. And since we have 2 for the coefficient of Hi, this will be 2x. So far, we have our initial concentrations and we have our change in concentrations. Now we add each of these columns together to determine the equations we will use for the final equilibrium concentrations. So for H2, it would be 1.50 minus x. For I2, it would be 1.50 minus x. And for HI, 0 plus 2x is just 2x. The values for E is what we will use to build our expression for Kc. So Kc equals the concentration of Hi squared over the concentration of H2 and I2. Now we plug in our values. We're given a value of Kc to be 50.5. Now pulling in the values from our E row of the ICE table, we have 2x squared for Hi over 1.50 minus x times 1.50 minus x. Doing the math, we have 50.5 equals 2x squared over 1.5 minus x squared. This gives us a perfect square. So what we can do is take the square root of both sides to get rid of the square on the right. The square root of 50.5 is 7.106335. I think that's enough numbers for rounding purposes. And this will be over 2x divided by 1.50 minus x. Now you want to solve for x. I will start by multiplying both sides by 1.50 minus x so that I could cancel this out at the bottom. These will cancel, leaving, and I'm going to bring this up here for room. 1.50 minus x times 7.106335 equals 2x. Now distributing the 7.106335 to the x, in 1.50, we have 10.6595 minus 7.106335x equals 2x, which will give 10.6595 equal to 9.106335x. Dividing both sides by 9.106335 gives x to equal 1.17 to 3 significant figures. Now we will use X to find the concentration of each substance by plugging it into each of these three equations. So your concentrations of H2 and I2 at equilibrium is 1.50 minus X, which is 1.50 minus 1.17, which is equal to 0.33 molar. And the concentration for HI at equilibrium is 2 times X, which is 2 times 1.17, and that gives us an equilibrium concentration of 2.34 molar. This next question asks us to calculate the equilibrium concentration of all species if 3.00 moles of N2 and 6.00 moles of O2 are placed in a 3.00 liter container, and it gives us the Kc of 1.5 times 10 to the second. The amount of N2 and O2 are given to us in moles, and remember it has to be molar in order to plug into our equilibrium expression. And we can convert this into molar by dividing moles per liter. So for O2, we have 6.00 moles into 3.00 liters, which gives 2 molar. And for N2, there is 3.00 moles in 3.00 liters, which gives 1 molar. Now, to figure out the change in concentration and the concentrations at equilibrium, we're going to use an ICE table. ICE, initial change and at equilibrium. The initial concentration for N2 is 1 molar and the initial concentration for O2 is 2 molar. We do not have an initial concentration for NO because the reaction is just beginning. So we have not formed the products yet, and that would be a 0. Therefore, since we do not have any products, the reaction will favor the forward direction of the formation of the product. So that change will be a positive, and that means that the concentrations of our N2 and O2 will decrease, and that change will be a negative. Now, by how much, we look at our coefficients. The coefficient for our product NO is 2. So we'll have a positive 2x, and the coefficient for our O2 is 1, so that will be 1x, and the coefficient for N is 1, which will be, N2 is 1, which will also be a 1x. Now, determine how we will calculate our equilibrium concentrations or our concentrations at equilibrium. We will add the I and the C in each row. So for N2, that will be 1 minus x. For O2, that will be 2 minus x. And for NO0 plus 2x is just 2x. Now that we have our initial concentrations, I'm going to get rid of this because I'm going to need that space. Now our Kc is going to be our products over our reactants. So our product is NO raised to the second over N2 raised to the 1 and O2 raised to the 1. We are given a value for Kc, which is 1.5 times 10 to the second, and we're going to plug in the values from my equilibrium row into our equation. So we have 2x raised to the second power, and we have 1 minus x and 2 minus x. 1 minus x for N2 and 2 minus x for O2. Unfortunately, in this case, we do not have a perfect square, so we're going to have to use the quadratic equation throughout. In solving for x, I'm going to multiply both sides by 1 minus x and 2 minus x. And this is to get rid of the fraction on one side. So I will have 1.5 times 10 to the second times 1 minus x times 2 minus x equals, and if I go ahead and square 2 times x, I have 4x squared. Now to multiply these two, I'm going to use the FOIL method. So in writing this out, 1.5 times 10 to the second, and bring that down. So using FOIL, a positive 1 times a positive 2 will give 2. A negative x times 2 is negative 2x. A negative x times 1 is negative x. And negative x times negative x is positive x squared equals to 4x x squared. And to write this in a simplified way, 1.5 times 10 to the second is 2 minus 2x minus x is a minus 3x plus x squared equals 4x squared. So to get more room, I am going to rewrite our equation here because we will definitely need that, and then clear as much of this as I can and rewrite this at the top. And I noticed that I did not keep in my significant figures. If I'm keeping in my significant figures, this will be 1.00 because we have 0.00 for our liters, zero point zero 0.00 for our moles. This is 0.00, and then I'm going to add this into each area here. So this will be 2.00 minus 3.00x plus x squared equals 4x squared. And now I'm going to delete this, and we have more space to work. So the next thing would be to distribute 1.5 times 10 to the second to each value inside of the parentheses. And that will give 3.00 times 10 to the second minus 4.50 times 10 to the second x plus 1.50 times 10 to the second x squared equals 4x squared. Next, I want to move 4x squared to this side and set everything to 0. And remember, 1.50 times 10 to the second is larger than 4. So this will be 1.46 times 10 to the second x squared minus 4.50 times 10 to the second x plus 3.00 times 10 to the second equals 0. At this point, because this is not a perfect square, I am going to have to follow my quadratic equation of ax squared plus bx plus c equals 0. And in order to solve this for x, we will have negative b plus or minus the square root of b squared minus 4ac all over 2a. And if we're looking at this format, we can pull out what will be a, b, and c. A is the value in front of the x squared, which is 1.46 times 10 to the second. B is going to be the value in front of x, which is negative 4.50 times 10 to the second. Remember to include your negative. And C will be the value in front of, or the value by itself with no x, which is 3.00 times 10 to the second. Now that we have our values for A, B, and C, and we have the equation we will plug in, I am going to write that second equation here. And my values for A, B, and C, because we need more space. Let me move this equation over here so we can have room to plug in our values, and then move the values up a bit to give us room to work. In plugging in our values, we have negative 4.50 times 10 to the second, plus or minus the square root of negative 4.50 times 10 to the second squared, minus 4, minus 1.46 times 10 to the second, times 3.00 times 10 to the second. And all of this will be over 2 times 1.46 times 10 to the second. Again, I cannot stress the importance of using parentheses wherever possible. And when you complete the calculations for both plus and minus, you will get x equals either 2.11 or 0.975. Now, if we plug 2.11 into either of these, the value comes out to be negative. We cannot have a negative. And the reason we can't have a negative is because it just don't make sense when you're talking about concentrations. So the value for x must be 0.975, which we will use to plug in to our equations for E to determine the concentrations of each of the substances in this chemical reaction. So the concentration of N2 is 1.00, including our significant figures, minus X, which is 1.00 minus 0.975, and that equals 0.0250 if we're doing it to three significant figures. The concentration of O2 is 2.00 minus x, which is 2.00 minus 0.975. And that gives a concentration of 1.03, which is to 3 sig figs. And the concentration of NO is 2x, which is 2 times 0.975, and that is 1.95. And each of these are molar. If this was helpful, please hit like and subscribe to know when more videos are coming out. And as always, thank you for watching.